Look up at the night sky. What do you see? A scattering of stars, the soft glow of distant galaxies, perhaps the steady arc of a planet moving through the darkness. But beneath that serene surface lies a secret. The universe is alive with motion, a breathtaking dance where chaos and order twirl together in perfect harmony. This is the dance of the cosmos, a celestial ballet that has shaped every atom, every star, and every galaxy since the dawn of time. It's a performance so vast, so intricate, that it defies human imagination, yet it's happening right above us every single night. Think of the most delicate balancing act you've ever witnessed. Now imagine that same precision playing out across billions of miles, where swirling nebulae collapse into newborn stars and planets glide along their orbits with clockwork precision. It's a paradox. The universe thrives on chaos, yet from that chaos emerges an astonishing order. How does something so turbulent give birth to such breathtaking symmetry? That's the mystery we're about to unravel. From the explosive birth of stars to the silent, gravitational embrace of black holes, this dance is the heartbeat of existence itself. This isn't just a story about distant galaxies or abstract forces, it's a story about us. Every element in your body, every breath you take, was forged in the crucible of this cosmic dance. The iron in your blood, the calcium in your bones, even the oxygen filling your lungs, all of it was once stardust, spun into being by the very forces we're about to explore. So join me on a journey through time and space, where we'll witness the universe's most dazzling performance. By the end, you'll never look at the night sky the same way again. The stage is set, the lights are dimmed, let's step into the grand theater of the cosmos. The universe doesn't choose between chaos and order, it embraces both, weaving them together into something far greater than either could be alone. Picture a nebula, that vast cosmic nursery where stars are born. It's a place of raw chaos with gas and dust swirling in violent turbulence, temperatures soaring to unimaginable heights, and shock waves rippling through space. Yet within that chaos, gravity begins to pull matter together, creating pockets of stability. Over eons, those pockets collapse into stars, their nuclear furnaces igniting with breathtaking precision. The same chaos that shatters also builds, sculpting celestial order from the storm. Now shift your gaze to our solar system, where planets glide along their orbits with such regularity we can predict their positions centuries in advance. This is order at its most elegant, a gravitational dance, so finely tuned that even tiny deviations could send worlds spiraling into disarray. But here's the twist, this order emerged from chaos. Billions of years ago, our solar system was a swirling disk of debris, a chaotic jumble of rock and gas. Through countless collisions and gravitational tugs, the chaos settled into harmony. The same forces that once scattered now bind, proving that chaos isn't the absence of order, it's the crucible where order is forged. Ancient skywatchers sensed this duality long before telescopes or equations could explain it. They marveled at comets, those unpredictable wanderers streaking across the heavens like fiery messengers of disorder. Yet they also mapped the steady rhythms of the planets, charting their paths with painstaking accuracy. To them, the cosmos was both a tempest and a timepiece, a paradox they could feel but not yet fathom. Today, we understand that quantum fluctuations, tiny, random ripples at the smallest scales, can shape the fate of galaxies, while black holes, those ultimate agents of chaos, also anchor entire galactic structures with their immense gravity. The universe thrives on this balance, a dance where every step of disorder is answered by a turn toward symmetry. So what holds it all together? The answer lies in the invisible hand of gravity, the great choreographer of the cosmos. It tames chaos without extinguishing it, allowing stars to explode even as it keeps galaxies intact. It's why swirling nebulae can birth solar systems, and why planets don't simply drift into the void. This delicate equilibrium isn't just a cosmic curiosity, it's the reason we exist. Without the interplay of chaos and order, there would be no stardust to form our bodies, no stable Earth to call home. The universe dances, and we are its fleeting, grateful witnesses. Deep within the swirling darkness of a molecular cloud, something extraordinary happens. These vast cosmic cauldrons, filled with gas 100 times colder than the frozen void of space, should be places of perfect stillness, yet they're anything but. Here, chaos reigns supreme. Turbulence rips through the cloud like invisible hurricanes, fracturing it into dense knots of matter. Gas and dust collide in unpredictable ways, building pressure, building heat, until gravity seizes its chance. What was once disordered and wild suddenly becomes focused, inevitable. A single dense core collapses, temperatures skyrocket, and in a flash of light that can outshine entire galaxies, a star is born. This isn't destruction, it's creation. The very same chaos that tears these clouds apart also provides the raw materials for new worlds. Take the Orion Nebula, that glowing masterpiece in our night sky. Through telescopes, we see a scene of breathtaking violence. Supersonic winds from newborn stars carving vast cavities in the gas, shockwaves rippling outward like cosmic thunder. Yet look closer. Amid the turmoil, hundreds of young stars emerge, many aligned in graceful arcs as if guided by an unseen hand. The chaos didn't hinder their birth, it made it possible. The secret lies in balance. Too much turbulence, and the cloud shatters before stars can form. Too little, and the gas remains diffuse, never reaching the critical density needed for ignition. The universe walks this knife edge perfectly, using chaos not as an enemy of order, but as its architect. Even the nuclear fusion at a star's core, that steady, rhythmic process that fuels its light, began with a chaotic collapse. The same primal forces that once scattered matter now bind it together in a brilliant, enduring glow. And the story doesn't end there. When massive stars die in supernova explosions, the most chaotic events imaginable, they blast heavy elements across space, seeding future generations of stars and planets. The calcium in your teeth, the gold in a wedding ring, the silicon in computer chips, all were forged in these violent final moments. Chaos, it turns out, isn't just a creative force. It's the artist's brush, the sculptor's chisel, the unseen hand that shaped everything from distant galaxies to the very atoms in your body. Without it, the universe would be a still and silent void. Instead, it thrums with light, with motion, with possibility, all because chaos and order learned to dance together. Planetary orbits are the universe's most elegant proof that chaos and order aren't opposites, they're partners. Picture Earth's journey around the Sun, a loop so precise we set our calendars by it. Johannes Kepler cracked the code 4 centuries ago when he discovered planets don't move in perfect circles, but in graceful ellipses, their speed subtly changing as they swing closer or farther from their star. It's a cosmic waltz governed by unshakable rules, where gravity's pull and orbital momentum balance so perfectly that a fraction more force would send worlds careening into space. But here's the twist, even this clockwork precision isn't immune to chaos. Jupiter, our solar system's gravitational titan, tugs gently on neighboring planets like a mischievous dancer pulling partners slightly offbeat. Over millions of years, these tiny nudges accumulate, reshaping orbits in ways no equation can perfectly predict. Take Mercury. Its path shifts minutely with each lap around the Sun, not just from Jupiter's influence but from relativity itself. as the warping of spacetime near our star alters its trajectory. Einstein's genius revealed that even Newton's pristine laws had hidden chaos woven into their fabric. Yet this delicate interplay is what makes planetary systems so resilient. When asteroids or comets stray too close, their chaotic paths often get redirected by larger planets rather than colliding with Earth. Jupiter acts as a cosmic shield, its gravity flinging potential hazards away like a bouncer clearing the dance floor. And when our solar system first formed, it was chaos that sculpted today's order: collisions between protoplanets, gravitational shoves from passing stars, and the drag of swirling gas all worked together to settle worlds into their current stable rhythms. The lesson is profound. Stability isn't the absence of disturbance, but the ability to absorb it. Saturn's rings, those dazzling bands of ice and rock, are constantly jostled by its moon's gravity, yet they maintain their symmetry. Uranus rolls on its side from some ancient impact, yet its seasons still unfold with dependable regularity. Even the Oort cloud, that vast shell of icy debris at our solar system's edge, dances between chaos and order, its objects drifting randomly until a passing star's gravity briefly organizes their path. So next time you hear about an exoplanet orbiting a distant star, remember, its perfect ellipse is no accident. It's the result of eons of gravitational negotiation, where chaos and order found equilibrium. The universe doesn't eliminate randomness, it harnesses it, turning turbulence into rhythm and chance into harmony. Our solar system's quiet reliability isn't despite the chaos around it, but because of it. Galactic spirals are the universe's grandest demonstration of harmony born from discord. Take the Milky Way, our celestial home. From afar, its spiral arms unfurl with breathtaking symmetry, tracing a pattern so precise it mirrors the golden ratio found in sunflowers and cyclones. But zoom in closer, and those same arms reveal a riot of activity. Stars ignite and die in unpredictable bursts, stellar nurseries churn with turbulent gas, and gravitational tugs from neighboring galaxies send ripples through the delicate structure. This isn't a flaw in the design, it's the design itself. The secret lies in what astronomers call the density wave theory. Imagine a traffic jam on a cosmic scale. As stars and gas move through the spiral arms, they slow down, bunching together like cars on a highway. This compression triggers star formation, lighting up the arms in brilliant blue clusters. Yet the individual stars don't stay trapped, they eventually drift out while new ones enter, creating an illusion of stability amid constant change. It's a dance of arrival and departure, where chaos fuels the very beauty we admire. Then there's the enigma of dark matter, the invisible scaffold holding it all together. Without it, spiral galaxies would fly apart. Stars orbit the galactic center so fast that visible matter alone couldn't keep them bound. Dark matter's gravitational embrace, unseen but undeniable, flattens the rotation curve, ensuring outer stars move just as swiftly as inner ones. Here, order emerges from the unknown, a silent force balancing the galaxy's fiery chaos. And let's not forget supernova, those catastrophic stellar explosions. They seem like pure chaos, yet they're essential architects of galactic evolution. A single detonation can compress nearby gas clouds, sparking new star birth, while scattering heavy elements like iron and oxygen across the cosmos. Our own solar system likely formed from debris enriched by such an explosion. The spiral galaxy, then, isn't just a structure, it's a dynamic engine where destruction and creation are two sides of the same coin. What's truly mesmerizing is how this balance plays out across the universe. From the whirlpool galaxy's perfect arms to the turbulent beauty of the pinwheel, each spiral tells the same story. Chaos doesn't unravel order, it renews it. The next time you gaze at the Milky Way's faint band across the night sky, remember, you're witnessing a masterpiece in motion, where every explosion, every collision, every invisible tug of gravity is part of an epic, eternal dance. Black holes are the universe's ultimate paradox, monuments to destruction that somehow sculpt the cosmos into order. Picture a star drifting too close to one of these gravitational behemoths. In an instant, the black hole's tidal forces stretch and compress it like taffy, shredding it into a glowing stream of plasma in a process called spaghettification. It's chaos incarnate, an act of violence so extreme it defies earthly analogies. Yet within that maelstrom, something remarkable happens. The debris doesn't just vanish, it spirals into the black hole's accretion disk, a swirling vortex of superheated matter moving at near light speed. And here's the twist, that disk often glows with near-perfect symmetry, its energy radiating outward in precise mathematical patterns. Now zoom out to the galactic scale. At the heart of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole. These cosmic titans weigh millions or even billions of times more than our Sun, and their gravity isn't just destructive, it's architectonic. Stars hundreds of light years away orbit these invisible monsters in stately, predictable paths. Without their anchoring presence, galaxies would lose their shape, their stars scattering like leaves in a storm. The supermassive black hole in galaxy M87, famously photographed by the Event Horizon Telescope, exemplifies this duality. Its shadow is ringed by a halo of light so geometrically perfect it could have been drawn with a compass, a stunning contrast to the unfathomable chaos at its core. Even black holes' most terrifying trait, their inescapable event horizons, reveals hidden order. The laws of thermodynamics, those bedrock principles governing energy and entropy, hold fast even here. As matter crosses the horizon, a black hole's temperature and spin adjust with precise predictability. Stephen Hawking's groundbreaking work showed they even emit radiation, slowly evaporating over eons in a process that ties quantum mechanics to gravity. This isn't random annihilation, it's chaos channeled through the universe's deepest laws. Perhaps the most poetic proof of black holes' dual nature lies in gravitational waves. When two of these monsters collide, they shake spacetime itself, sending ripples across the cosmos. The signal detected by LIGO in 2015 wasn't noise. It was a clean, rising chirp, its frequency and amplitude matching Einstein's equations to perfection. From a cataclysm that warps time and snaps stars like twigs, emerges a ripple of exquisite mathematical purity. So are black holes agents of chaos or enforcers of order? The answer, like so much in the cosmos, is both. They devour, yes, but in doing so, they sculpt galaxies, tune the universe's constants, and even, in their final moments, whisper secrets about the quantum fabric of reality. They're the darkest dancers in the cosmic ballet, proving once again that destruction and creation aren't opposites. They're partners, twirling together in the grandest performance of all. Dark matter is the universe's greatest unsung architect, an invisible force weaving order into the cosmic tapestry without ever revealing itself. Imagine a spider's web glistening with dew at dawn. You see the delicate strands, the symmetrical pattern, but not the spider who spun it. Dark matter works the same way. Its gravity sculpts galaxies into vast, interconnected filaments, a sprawling cosmic web stretching across billions of light years. Galaxies don't drift randomly through the void. They cluster along these invisible threads like pearls on a necklace, drawn together by something we can't see. Here's the mystery: dark matter doesn't interact with light. It doesn't absorb, reflect, or emit a single photon, yet its gravitational grip is undeniable. Stars at the edges of spiral galaxies orbit so fast that without dark matter's unseen mass anchoring them, they'd be flung into the abyss. The Milky Way's outer stars, for instance, move at speeds that defy the laws of visible matter alone. It's as if an invisible hand holds them in place, balancing chaos with silent precision. But dark matter isn't just a cosmic glue, it's also a chaotic frontier of modern physics. We don't know what it's made of. Is it a sea of exotic particles lighter than an atom yet vastly more numerous? Or could it be primordial black holes, remnants of the universe's fiery birth? Theories abound, but the evidence remains elusive. Even the Large Hadron Collider, humanity's most powerful particle smasher, hasn't detected a whisper of dark matter's true nature. Yet its influence is everywhere. When astronomers map the universe on the grandest scales, they find dark matter's fingerprints in the way galaxy clusters collide. Take the Bullet Cluster, where two clusters slammed together like titans. The visible gas, hot and turbulent, piled up in the wreckage, but the bulk of the mass, traced by gravitational lensing, sailed right through. The dark matter barely noticed the collision, revealing its ghostly dominance. This unseen force doesn't just hold galaxies together, it shaped their very existence. In the early universe, tiny fluctuations in dark matter's density acted as gravitational seeds. Ordinary matter, drawn to these invisible wells, eventually ignited into stars and galaxies. Without dark matter's scaffolding, the cosmos might have remained a formless haze. So while stars and planets command our gaze, dark matter works in the shadows, a silent choreographer in the cosmic dance. It's a reminder that the universe's most profound order often lies just beyond our sight, waiting to be understood. Every spiral galaxy's graceful turn, every cluster's perfect alignment, they're all part of a masterpiece we're only beginning to decode. At the smallest scales imaginable, the universe defies every expectation of order. In the quantum foam, particles flicker into existence and vanish again in a ceaseless dance of uncertainty. A single electron isn't just a tiny dot, it's a blur of probabilities, here one instant and gone the next. This isn't theoretical guesswork, scientists have measured it. Even in a perfect vacuum where nothing should exist, space itself crackles with energy, birthing particle-antiparticle pairs that annihilate in fractions of a second. It's chaos at its purest, a microscopic carnival of randomness. Yet here's the astonishing truth. This quantum chaos built the cosmos. Those fleeting fluctuations, trillions of times smaller than an atom, left their mark on the oldest light in existence, the cosmic microwave background. That faint glow, the afterimage of the Big Bang, isn't perfectly smooth. It's speckled with temperature variations, tiny hotspots and cold spots that mirror the quantum jitters of the universe's infancy. Over billions of years, gravity amplified those minute differences. Denser regions pulled in more matter, growing into galaxies, while emptier stretches became cosmic voids. The Milky Way, the Andromeda Galaxy, even the vast Laniakea supercluster, all owe their existence to quantum randomness. Consider the implications. A fluctuation 1/billionth the size of a proton could determine where a galaxy cluster forms. It's like rolling a trillion-sided die at the dawn of time, with each outcome shaping the fate of millions of stars. The universe didn't erase this chaos, it embraced it, weaving unpredictability into the fabric of reality. Even now, quantum fluctuations influence the formation of new stars, the spin of black holes, and the distribution of dark matter, the most poetic part. We're made of this chaos. Every atom in your body was once part of a quantum ripple that grew into a star, which later exploded, scattering its enriched remains across space. The same uncertainty that governs electrons in a lab also wrote the story of your existence. So when you gaze at the night sky, you're not just seeing distant lights, you're witnessing quantum randomness magnified across cosmic time, a testament to how deeply chaos and order are entwined. A single grain of cosmic dust drifting through the void seems insignificant until it collides with a comet. That microscopic impact alters the comet's trajectory ever so slightly, shifting its path by less than the width of an atom. Yet over centuries, that tiny nudge grows. The comet swings closer to the sun, heats up and fractures, scattering debris across its orbit. Fast forward millennia, and Earth plows through that same debris field, igniting a meteor shower that lights up the night sky. What began as an imperceptible tap becomes a celestial light show, all because of one speck of dust. This is the butterfly effect on a cosmic scale, where minute changes ripple outward with astonishing consequences. Take our solar system's delicate balance. Jupiter, with its colossal gravity, acts as a cosmic shepherd. Its slightest gravitational tugs nudge asteroids away from inner planets, including Earth. Without this subtle guidance, our world might face catastrophic impacts every few centuries instead of every few million years. The dinosaurs' fate, sealed by a 6-mile-wide asteroid, could have been a recurring nightmare. Instead, Jupiter's quiet influence grants Earth the stability needed for life to flourish. Now zoom out to the grand dance of galaxies. A star drifting slightly off course in the Milky Way's crowded core might seem inconsequential. But over billions of years, that star's gravity tugs on neighboring stars, which tug on others, reshaping entire spiral arms. Astronomers running simulations watch in awe as minuscule starting differences, a star's position shifted by a hair's breadth, lead to wildly divergent galactic futures. One simulation might show a serene spiral, another a violent collision. The universe remembers every tiny change, amplifying them into cosmic turning points. Even the cosmos' largest structures bear the fingerprints of small beginnings. The Big Bang didn't create a perfectly uniform universe. It left behind quantum ripples no larger than a billionth of a proton. Today, those ripples have stretched into vast galaxy clusters and empty voids spanning millions of light years. The slightest variation in those early fluctuations determined whether a region would become a supercluster or a cosmic desert. So what's the lesson? The universe isn't just interconnected, it's hypersensitive. A comet's path, a star's drift, even a quantum flicker at the dawn of time, none of these events fade into oblivion. They're woven into the cosmos' unfolding story, proving that chaos isn't randomness, it's a web of invisible threads, each tug shaping eternity. When you wish upon a shooting star tonight, remember, you're witnessing the echo of a choice the universe made long ago, one infinitesimal nudge at a time. A star's final moments are anything but quiet. When a massive star exhausts its nuclear fuel, its core collapses in less than a second, triggering an explosion so powerful it can outshine an entire galaxy. This is a supernova, a cataclysm of unimaginable violence, where temperatures soar to 100 billion degrees and shockwaves rip through space at millions of miles per hour. Yet within this maelstrom lies a paradox. The very forces that obliterate a star also forge the building blocks of life. Take the Crab Nebula, that ghostly remnant glowing in the constellation Taurus. At its heart spins a pulsar, a neutron star no larger than a city, yet denser than the sun. It rotates 30 times per second, sending out beams of radiation with metronomic precision. This is order carved from catastrophe. The pulsar's birth was chaos incarnate, but its existence now provides a cosmic lighthouse. Its rhythm so reliable we've used it to test Einstein's theory of relativity. Surrounding it, the nebula's tangled filaments shimmer with heavy elements: iron, nickel, even gold. all forged in the supernova's furnace and scattered across light years of space. Those scattered atoms don't just drift aimlessly. Gravity gathers them into new molecular clouds, where they'll eventually coalesce into planets, asteroids, and perhaps even life. The iron in your blood, the calcium in your bones, the gold in your jewelry, all were once stardust, hurled into the void by a dying star billions of years ago. Without these explosions, the universe would be a far simpler place, just hydrogen and helium drifting through an eternal twilight, with no planets, no chemistry, no possibility of life. Supernovae don't just spread elements, they shape the very architecture of galaxies. The shock waves from these explosions compress nearby gas clouds, triggering the birth of new stars. It's a cosmic chain reaction. Death sparks life, which in turn leads to more death and rebirth. The Orion Nebula, that stellar nursery visible to the naked eye, was likely jump-started by a supernova's violent push. Even Earth's history bears their mark. Some scientists believe a nearby supernova explosion may have triggered a mass extinction millions of years ago, clearing the way for mammals to rise. So the next time you look up at the night sky, remember, the darkness isn't empty. It's a graveyard and a nursery, a place where endings and beginnings are forever entwined. The same explosions that erase stars also write the next chapter of the cosmos, scattering the ingredients for worlds yet unborn. Destruction and creation aren't opposites, they're partners in the universe's grand, unending dance. Exoplanets have shattered our cosmic assumptions, revealing planetary systems that defy the orderly model of our own solar neighborhood. Take TRAPPIST-1, that dim red dwarf star 39 light-years away. Its 7 rocky worlds orbit with such perfect synchronicity that their gravitational tugs create a rhythmic pattern, like interlocking gears in a celestial clock. For every 2 orbits the innermost planet completes, the next one finishes 3, the next 4, and so on up the chain. This precise resonance keeps their dance stable across billions of years, a delicate balance where chaos could easily reign. Yet just a cosmic stone's throw away in the grand scheme. Other systems mock such harmony. Consider the enigma of hot Jupiter's gas giants that orbit blisteringly close to their stars, completing laps in mere days. These shouldn't exist according to old planetary formation theories. Gas giants were thought to take shape in the cold outer reaches of a system, where ices and gases could accumulate. Yet here they are, parked practically atop their stars like overeager dance partners. The leading theory, they migrated inward, caught in a gravitational tug of war with leftover disk material or neighboring planets. Some may have been flung into chaotic spirals before settling into scorching orbits, while others might have swapped places in planetary pile-ups. Then there are the real rebels, planets orbiting binary or even triple-star systems. Picture Kepler 16b, a world with 2 suns in its sky like a real-life Tatooine. The competing gravitational pulls from its stellar hosts should tear such planets apart, yet they persist, finding precarious stability in the Lagrange points, those cosmic sweet spots where forces balance. Other exoplanets endure even wilder rides, like HD 8666b, which experiences extreme seasonal swings as its eccentric orbit sends it hurtling close to its star before flinging it back out. What's truly revelatory is how these discoveries rewrite the rules. Our solar system, once the archetype of planetary order, now looks like just one variation in a vast symphony of possibilities. Some systems resemble ours with small inner planets and gas giants farther out. Others flip the script entirely, with super-Earth rocky worlds up to 10 times Earth's mass, crowding close to their stars while ice giants lurk in the darkness. And then there are the rogue planets untethered to any star, drifting through interstellar space like cosmic nomads. Yet amid this diversity, patterns emerge. Resonant orbits like TRAPPIST 1 suggest that even in alien systems, chaos often gives way to order over time. Migration theories explain hot Jupiters not as anomalies but as products of dynamic youth. Binary star systems prove that planets can adapt to extreme environments, finding stability where none seems possible. Every new exoplanet discovered adds another verse to the universe's grand song, one where chaos composes the melody, but order provides the rhythm. The lesson is clear: the cosmos doesn't play by our rules. It invents its own, then dances to them without looking back. The Oort cloud is the solar system's final frontier, a vast, ghostly shell of icy remnants stretching nearly a light year into the void. Unlike the orderly orbits of planets or even the scattered debris of the Kuiper belt, this distant realm operates by its own chaotic rules. Here, billions of frozen objects drift in slow, unpredictable paths, so loosely bound to the sun that a passing star's gentle nudge can send them careening inward as comets. These aren't the polite, short-period visitors like Halley's Comet, which returns like clockwork every 76 years. Oort cloud comets are the wild cards, appearing without warning, their orbits stretched into extreme ellipses that can take millions of years to complete. Consider the case of Comet Hale-Bopp, which lit up Earth's skies in 1997. Its journey began in the Oort cloud's depths, where it slumbered for eons until some distant gravitational whisper, perhaps from a star we'll never identify, sent it tumbling toward the inner solar system. By the time it reached us, its nucleus was a 25-mile-wide ball of ice and dust, glowing with a brilliance visible even from city streets. But here's the twist: Hale-Bopp's chaotic origins didn't make it a destructive force. Instead, its volatile ices vaporized in the sun's heat, creating a spectacular tail that stretched halfway across the sky. Chaos, it turns out, can be breathtakingly beautiful. Yet the Oort cloud's influence runs deeper than occasional celestial fireworks. Astronomers believe it's a frozen archive of the solar system's earliest days, preserving pristine material untouched since the planets formed. When a comet like Hale-Bopp or the recent comet Neowise streaks past, we're not just watching a cosmic light show, we're glimpsing ingredients older than Earth itself. These icy wanderers carry molecules like water, carbon dioxide, and even complex organic compounds, the same building blocks that may have seeded our planet with the precursors to life. The Oort cloud's existence also hints at the solar system's turbulent youth. Most of its objects weren't born there. They were flung outward by the gravitational slingshots of young gas giants, a celestial game of pinball that left them stranded in the deep freeze. Today, they drift like forgotten relics, their orbits so easily disturbed that even the Milky Way's tidal forces can shake them loose. It's a delicate balance, one that transforms the solar system's outermost reaches into a cosmic game of chance, where chaos and gravity conspire to send ancient ice balls hurtling toward the sun. So the next time you see a comet's tail painted across the night sky, remember, you're witnessing more than a random visitor. You're seeing a messenger from the solar system's farthest, wildest edge, a place where order and disorder dance on the knife's edge of gravity's grasp. Imagine the fabric of space and time as a tranquil lake, its surface smooth and undisturbed. Now picture two massive black holes spiraling toward each other, their immense gravity churning the waters. As they merge in a final, violent embrace, they send waves rippling outward not through water but through space-time itself. These are gravitational waves, the universe's most dramatic way of announcing a cosmic collision. When LIGO, the Laser Interferometer Gravitational Wave Observatory, first detected these ripples in 2015, it wasn't just a scientific triumph, it was humanity tuning in to the universe's hidden soundtrack. What's astonishing isn't just the detection, but what these waves reveal. the signal from that first black hole merger, WGW150914, lasted barely 0.2 of a second. Yet in that fleeting moment, physicists extracted a wealth of information. The wave's frequency and amplitude betrayed the black hole's masses 29 and 36 times that of our Sun, and their spins, which were whirling at half the speed of light. This wasn't noise, it was a finely tuned cosmic fingerprint, a precise mathematical signature encoded in chaos. The beauty lies in the contrast. The merger itself was cataclysmic, releasing more energy in gravitational waves than all the stars in the observable universe combined emit as light. Space itself shuddered, warping and recoiling like a drumhead struck by unimaginable force. Yet the waves that reached Earth, after traveling 1.3 billion light-years, matched Einstein's century-old predictions with uncanny accuracy. The most violent event imaginable obeyed the universe's strictest rules, proving that even chaos has a hidden grammar. Gravitational waves don't just tell us about black holes. They're rewriting the cosmic map. When neutron stars collided in 2017, the resulting waves carried clues about their composition, confirming these ultra-dense objects forge heavy elements like gold and platinum. Future detectors like the space-based LISA mission could unveil mergers from the universe's first billion years, probing an era before stars or galaxies existed. Each ripple is a messenger carrying secrets from the darkest, most chaotic corners of reality. So the next time you hear about gravitational waves, don't just think of them as cosmic tremors. Think of them as the universe's way of balancing its books, a reminder that even in the most violent encounters, order prevails. The chaos of colliding black holes becomes a symphony when we learn to listen, each note a testament to the cosmos' unshakable logic. The universe hums with possibility, billions of galaxies, each home to billions of stars, many circled by planets in life-friendly orbits. Given such abundance, the cosmos should be a bustling metropolis of civilizations, their signals crisscrossing the void. Yet when we listen, all we hear is silence. This eerie absence is the Fermi paradox, a mystery that cuts to the heart of our place in the universe. If chaos and order dance so elegantly to create stars, planets, and even life on Earth, why does the grand stage seem empty? One possibility is that chaos wins in the end. The universe may be brimming with potential, but it's also a shooting gallery. Gamma ray bursts, cosmic lightning bolts from dying stars, could sterilize entire galaxies in an instant. Rogue asteroids or comets might strike planets with clockwork regularity, resetting the evolutionary clock just as life begins to stir. Even a planet's own geology can turn against it, with supervolcanoes or shifting magnetic fields dooming fledgling ecosystems. The path from stardust to civilization is littered with pitfalls, and most worlds may never make it past the first act. Then there's the darker alternative. Order itself could be the obstacle. Intelligence might carry the seeds of its own destruction. A civilization advanced enough to broadcast its presence could also possess the means to wipe itself out, whether through war, environmental collapse, or technology spiraling beyond control. The same ingenuity that unlocks the stars could build the traps that silence them. This is the Great Filter, a theoretical barrier that prevents life from reaching interstellar scales. If it lies ahead of us, our future may be bleak. If it lies behind, we might already be the rarest of cosmic miracles, but not all explanations are so grim. Some argue the silence is an illusion, a matter of scale. The Milky Way alone spans 100,000 light-years. A civilization broadcasting radio waves just a few centuries ago would still be invisible to us. Their signals haven't had time to cross the void. Others suggest advanced societies might abandon noisy technologies, fading into stealth modes we can't yet detect. Imagine ants speculating about human cities while standing next to a fiber optic cable. They'd see no evidence of us, though we're all around them. Perhaps the answer lies in patience. The universe is 13.8 billion years old, but Earth-like planets may have only emerged in the last few billion. We could be among the first, with others still evolving in distant cradles. Or maybe life thrives in forms so alien we don't recognize it, floating in gas giants' atmospheres, swimming in subsurface oceans, or even existing as pure energy. The truth might not be absence, but our own limited vision. The Fermi paradox isn't just about aliens, it's a mirror. It forces us to confront whether intelligence is a fleeting spark or an enduring flame. Are we alone because chaos snuffs out life faster than it can bloom? Or is the universe waiting for us to prove that order, creativity, and curiosity can outlast the chaos? The answer, when it comes, will tell us not just who else is out there, but what kind of future we might expect for ourselves. Until then, the silence remains our most profound cosmic riddle. Dark energy is the universe's quiet revolutionary, an unseen force working against gravity's tireless efforts to hold everything together. While gravity pulls galaxies into clusters and superclusters, dark energy pushes them apart, accelerating the expansion of space itself. Picture a balloon inflating faster and faster, not because someone's blowing harder, but because the rubber itself is stretching more vigorously with each passing second. This isn't just theoretical. In 1998, astronomers studying distant supernova made a startling discovery. The universe's expansion isn't slowing down as everyone expected. It's speeding up, and the culprit, a mysterious repulsive force we now call dark energy. What makes dark energy so baffling is its origin. One leading theory points to quantum vacuum fluctuations, tiny, chaotic bursts of energy popping in and out of existence in empty space. According to quantum mechanics, even a perfect vacuum isn't truly empty. It's a seething foam of virtual particles, appearing and vanishing in fractions of a second. Normally, these fluctuations cancel each other out, but on cosmic scales, they might add up to something far grander, a relentless pressure stretching space-time itself. It's chaos at the smallest scales driving change at the largest, a paradox Einstein himself might have struggled to reconcile. The consequences are both subtle and staggering. On one hand, dark energy's gentle push shapes the cosmic web, that vast network of galaxies threaded along invisible filaments. Without it, gravity would have drawn matter into denser, more crowded structures long ago. On the other hand, if dark energy's strength increases over time, it could lead to a fate known as the Big Rip. In this scenario, the accelerating expansion would eventually overpower every force in nature, first tearing galaxies apart, then stars from their systems, and finally atoms themselves. The universe would end not with a crunch, but with a silent, irreversible unraveling. Yet for now, dark energy is a balancing act. Its repulsive force is precisely tuned to counteract gravity's pull, creating a cosmic tension that allows galaxies to form while still driving them apart. Some theorists suggest this balance isn't accidental, that dark energy's value is fixed by deeper laws we haven't yet uncovered. Others propose it's a temporary phase, a fluctuation in a much longer cycle of expansion and contraction. What's certain is that dark energy reminds us how little we truly understand. It makes up 68% of the universe's total energy, yet we can't see it, touch it, or even explain it fully. It's the ultimate wild card in the cosmic dance, a force that could one day dissolve all order into chaos, or perhaps reveal a deeper harmony hidden in the fabric of reality. The universe, it seems, still has secrets to share. The idea of a multiverse stretches the cosmic dance between chaos and order to mind-bending new scales. Picture not just one universe, but an infinite tapestry of them, each with its own unique set of physical laws, its own destiny written in the fabric of space-time. In some, gravity might be too weak to pull matter together, leaving only a thin, lifeless haze. In others, the forces binding atoms could be so strong that stars ignite and burn out in mere millennia. The sheer variety is dizzying. Universes that flicker into existence and vanish in an instant, others that expand so rapidly they become cosmic deserts, and a rare few like ours Goldilocks realms where conditions are just right for galaxies, planets, and life. What's fascinating isn't just the randomness of this cosmic lottery, but how order still finds a way. Even in a multiverse teeming with chaos, pockets of stability emerge. Think of it like a vast ocean where most waves crash and dissolve, but occasionally a perfect ripple forms, holding its shape just long enough to create something beautiful. Our universe is that ripple, the precise tuning of its constants, the strength of gravity, the mass of an electron, the energy binding atomic nuclei, forms a delicate web of balance. Tweak any one of these values even slightly and stars wouldn't shine, chemistry wouldn't function, and life as we know it would be impossible. Yet here we are in a universe that somehow got the recipe just right. The multiverse theory offers a provocative explanation for this fine-tuning. With infinite universes, every possible combination of laws gets a chance to play out. Most are inhospitable, but a handful, purely by chance, strike the perfect equilibrium. It's like rolling a trillion-sided die. Eventually, you'll land on the one outcome where everything clicks. This isn't just philosophical speculation. Some versions of string theory, like the landscape multiverse, suggest higher dimensions could harbor countless bubble universes, each with its own physics. Even cosmic inflation, the rapid expansion thought to have shaped our early universe, might generate endless pocket universes like bubbles in a boiling pot. Yet the multiverse doesn't erase the dance, it amplifies it. Within each viable universe, chaos and order continue their eternal interplay. Black holes devour matter while birthing new galaxies. Quantum fluctuations spark star formation. Dark energy stretches space-time while gravity stitches it together. The scale changes, but the rhythm remains. And if other universes harbor life, their inhabitants might gaze at their own night skies, marveling at the same delicate balance we do, each cosmos a unique verse in the same grand poem. The multiverse theory challenges us to rethink not just our place in space, but in reality itself. Are we the lucky winners of a cosmic dice roll, or is there a deeper principle guiding the universe toward order amid the chaos? Either way, one truth endures: the dance never stops. Whether in our universe or a trillion others, chaos and order will always twirl together, partners in the greatest performance of all. Time flows like a river, carrying the universe from order toward chaos with unshakable certainty. This is entropy, the silent force behind time's arrow, the reason ice melts in your glass and stars eventually burn out. The second law of thermodynamics states it plainly: in any closed system, disorder must increase. Yet here we are, surrounded by breathtaking complexity, spiral galaxies, beating hearts, symphonies of thought, all somehow thriving in this cosmic slide toward dissolution. How can such intricate order emerge when the universe insists on falling apart? Look at a snowflake forming in a winter cloud. Its delicate hexagonal symmetry seems to defy entropy, crystallizing perfect patterns from swirling chaos. But zoom out and you'll see the bigger picture. The energy released during that freezing process heats the surrounding air, increasing disorder elsewhere. The snowflake's beauty is a temporary loan against the universe's inevitable debt. Stars operate the same way. A nebula's collapse into a shining sun seems like order winning, until you account for the radiation flooding into space, the wasted heat, the eventual stellar death that scatters ashes across light years. Every local victory against entropy comes at a cost, adding to the cosmic tally of disorder. Life itself might be the ultimate rebellion against this trend. A single cell organizes thousands of chemical reactions with precision, building structures so complex they make supercomputers look crude. Forests regulate their own climates, and brains weave intangible thoughts from electrical sparks. But biology's order is no exception to entropy's rule, it's a workaround. Every living thing survives by exporting disorder, whether through exhaling carbon dioxide, shedding heat, or leaving waste in its wake. Earth's biosphere stays orderly because the sun showers it with energy, and life funnels that energy into structure before passing the disorder along like a hot potato. Now consider the grandest scale of all. The universe began in a state of near-perfect order, a hot, dense soup where particles were almost indistinguishable from one another. As space expanded, differences emerged. Gravity amplified tiny fluctuations, sculpting galaxies from what was once uniformity. In one sense, this created order: stars, planets, black holes, but in another, it was entropy's triumph. The early universe's simplicity gave way to complexity, and complexity is just another word for disorder's many possible arrangements. Even dark energy, that mysterious force accelerating cosmic expansion, might be entropy's final masterpiece, stretching space-time so thin that matter can no longer clump, ensuring maximum dispersal, maximum chaos. Yet within this inexorable march, pockets of meaning persist. A planet's magnetic field shields it from solar storms. DNA replicates with near-perfect fidelity. Civilizations build libraries to preserve knowledge against time's erosion. These aren't illusions, they're proof that entropy doesn't erase order, it redefines it. The universe isn't a clock winding down. It's a story unfolding where every chapter, no matter how fleeting, adds something irreplaceable to the whole. Our lives may be eddies in the stream, but for a brief, shining moment, we get to shape the current. Earth sits in the cosmic sweet spot, close enough to the sun to keep water liquid, but far enough to prevent it from boiling away into space. This Goldilocks zone isn't just a static band of real estate. It's a dynamic equilibrium where chaos and order perform their most delicate balancing act. Consider Mercury, scorched by solar radiation, or Mars, frozen and barren, both reminders of how slight shifts in distance or atmosphere can render a world lifeless. Yet Earth, through sheer cosmic luck and a symphony of stabilizing forces, has maintained this precarious perfection for billions of years. But just right isn't a guarantee, it's a negotiation. Our planet's climate has swung violently over eons, from snowball Earth, episodes where ice sheets reached the equator, to hothouse periods when palm trees grew in the Arctic. These extremes might seem like chaos run rampant, yet they're part of a larger order. Volcanic eruptions, for instance, spew carbon dioxide that warms the planet, while weathering rocks pull it back down, creating a thermostat more reliable than any human invention. Even asteroid impacts, those ultimate agents of disruption, may have cleared the stage for mammals to rise after the dinosaurs' reign ended. Chaos doesn't just threaten life, it refines it. What truly sets Earth apart is its arsenal of stabilizing mechanisms. The magnetic field, generated by molten iron swirling in the core, acts as an invisible shield, deflecting solar winds that would otherwise strip away our atmosphere. The moon's steady tug slows Earth's rotation, preventing wild day-night temperature swings, and the carbon cycle, a planetary scale recycling program, keeps greenhouse gases in check over millennia. These aren't accidents, they're the universe's way of weaving chaos into a safety net. The miracle isn't just that Earth found the Goldilocks Zone, it's that it stayed there. Venus, often called Earth's twin, likely once had oceans before a runaway greenhouse effect turned it into a hellscape. Mars, too, shows signs of ancient rivers, but without a magnetic field to protect its atmosphere, it became the frozen desert we see today. Our planet's resilience lies in its ability to absorb shocks without losing equilibrium, like a gyroscope that wobbles but never falls. And then there's water, the silent partner in this dance. Its unique properties, expanding when frozen, storing heat efficiently, dissolving countless compounds, make it the universe's best solvent for life. But water alone isn't enough. Europa, Jupiter's icy moon, harbors a subsurface ocean, while Saturn's Enceladus sprays geysers of water vapor into space. Yet without the right mix of energy, chemistry, and stability, these worlds remain potential rather than promise. Earth's true rarity isn't just location, it's timing, chemistry, and a touch of chaos that keeps the story going. So when we search for life beyond our solar system, we're not just hunting for planets in the habitable zone. We're looking for worlds that have danced the same tightrope, balancing cataclysm and calm long enough for complexity to emerge. The Goldilocks Zone isn't a place, it's a performance, one where chaos and order take turns leading, and life is the encore. Pulsars are the universe's ultimate comeback story, collapsing from stellar chaos into some of nature's most precise timekeepers. When a massive star goes supernova, its core doesn't just fade quietly. In that cataclysmic explosion, gravity crushes the remaining matter into a neutron star so dense that a teaspoonful would weigh as much as Mount Everest. But for some of these stellar remnants, the story doesn't end there. If the dying star was spinning rapidly before its collapse, and most are like cosmic figure skaters pulling in their arms, that rotation gets concentrated into an object no larger than a city, yet spinning hundreds of times per second. The result, a pulsar, nature's version of a lighthouse, sweeping beams of radiation across space with metronomic precision. What's astonishing isn't just their speed, but their reliability. The Crab pulsar, born from a supernova observed in 1054 AD, spins 30 times every second, and its pulses arrive with a consistency that rivals atomic clocks. These aren't minor fluctuations, we're talking about precision down to microseconds over decades. When NASA Voyager spacecraft carried pulsar maps into interstellar space, they weren't just artistic flourishes. Those diagrams actually work as cosmic GPS, with each pulsar's unique pulse pattern serving as an identifiable beacon across the galaxy. But pulsars do more than keep time, they're also laboratories for testing the universe's fundamental laws. When astronomers discovered the first binary pulsar system in 1974, they noticed something extraordinary. The pulsar's orbit was decaying by precisely the amount Einstein's theory of general relativity predicted, as it lost energy through gravitational waves. This was the first indirect evidence of ripples in spacetime, decades before LIGO direct detection. Even today, pulsars serve as cosmic scales, weighing distant planets when their pulses subtly shift from a world's gravitational tug. The real magic lies in their duality. A pulsar's birth is among the most violent events in the universe. A supernova's shockwave can outshine entire galaxies. Yet from that destruction emerges an object of exquisite regularity, its beams sweeping past Earth as predictably as a Swiss watch. Some, like millisecond pulsars, have been spun up even faster by siphoning material from companion stars, achieving rotations faster than a blender blade. Others, like the recently discovered Black Widow pulsars, are actively vaporizing their stellar partners with intense radiation. Perhaps most poetically, pulsars teach us that even in a universe sliding toward entropy, pockets of perfect order can emerge. Their steady pulses cut through interstellar static like cosmic Morse code, reminding us that chaos and precision aren't opposites, they're partners in an endless dance. Every time a pulsar's beam flashes across our telescopes, it's not just a dead star's heartbeat, it's proof that even the universe's most violent acts can give birth to something astonishingly precise. Beyond Neptune's orbit, where sunlight is a faint glimmer, lies a cosmic junkyard of frozen relics, the Kuiper belt. This vast donut-shaped region, stretching from 30 to 55 astronomical units from the Sun, is anything but random debris. Its icy inhabitants, including dwarf planets like Pluto and Haumea, follow orbits so aligned they trace near-perfect circles within a narrow plane, as if arranged by some celestial choreographer. This orderly arrangement is no accident, it's a fossil record of the solar system's infancy, preserved in deep freeze for 4.6 billion years. Look closer though, and the Kuiper belt reveals scars of ancient upheaval. Take Pluto and its largest moon, Charon, locked in a gravitational tango where both bodies orbit a shared point in space. This peculiar dance suggests a violent past, likely a colossal impact that shattered an earlier version of Pluto, leaving behind a system of moons and debris. Then there's Haumea, the rugby ball-shaped dwarf planet spinning so fast it completes a rotation every 4 hours, likely accelerated by a primordial collision that launched its 2 moons into space. These aren't quiet worlds, they're survivors of a chaotic era when the outer solar system was a demolition derby of icy bodies. The real intrigue lies in the Kuiper belt's resonant populations, objects whose orbits sync perfectly with Neptune's. For every 2 orbits Pluto makes around the Sun, Neptune completes 3, a gravitational harmony that keeps them forever aligned. This phenomenon, called a 2 to 3 resonance, isn't unique to Pluto. Thousands of objects share this stable rhythm, avoiding close encounters with Neptune through celestial timing as precise as a Swiss watch. Yet just beyond these orderly orbits lurk the scattered disk objects, like Eris, Pluto's rival in size, whose wild, tilted paths suggest they were violently ejected from the inner Kuiper belt during Neptune's migration outward. This duality between the Kuiper belt's clockwork patterns and its rogue outliers holds clues to the solar system's most dramatic reshuffling. Around 4 billion years ago, as Jupiter and Saturn fell into orbital resonance, their combined gravity likely sent Uranus and Neptune spiraling outward. Neptune's migration scattered icy bodies like cosmic billiard balls, some flung inward to become today's short-period comets, others hurled to the Oort cloud's distant reaches. The Kuiper belt's current structure is the aftermath of this upheaval, a snapshot of chaos frozen in time. Modern missions like New Horizons, which flew past Pluto in 2015 and Arrokoth in 2019, have transformed these icy worlds from blurry dots into geological marvels. Arrokoth, a contact binary resembling a cosmic snowman, shows no impact craters, hinting that the Kuiper belt's far reaches may preserve primordial building blocks untouched since the solar system's birth. Meanwhile, Pluto's nitrogen glaciers and mountain ranges of water ice reveal an active world where geology still shapes the landscape, despite temperatures near absolute zero. The Kuiper belt isn't just a graveyard of planetary leftovers, it's a time capsule waiting to be read. Every odd orbit, every craterless surface, every binary pair tells part of a story written in gravity and ice. As we discover more of these distant worlds, we're not just mapping the solar system's edge, we're decoding the opening chapters of its history, where chaos and order conspired to build the stable neighborhood we call home today. Magnetars are the universe's ultimate paradox, cosmic lighthouses born from chaos, wielding magnetic fields so powerful they rewrite the rules of physics. Imagine taking a neutron star, already one of nature's most extreme objects, and cranking its magnetic field up 1,000-fold. The result is a magnetar, where magnetism becomes a force of apocalyptic proportions. These stellar remnants don't just bend the laws of nature, they shatter them, generating fields strong enough to atomize matter from thousands of miles away and warp the very structure of space itself. The violence begins in their birth. When a massive star collapses into a neutron star, its magnetic field doesn't just compress, it twists, amplifying like a coiled spring until it reaches unimaginable intensities. Picture the entire magnetic output of a star like our Sun, squeezed into a sphere barely 12 miles across, spinning faster than a kitchen blender. This creates stresses so extreme that the neutron stars crust a crystalline lattice harder than diamond cracks under the strain like an eggshell. These starquakes release energy in sudden, catastrophic bursts, firing off gamma-ray flares that can outshine the entire Milky Way for a fraction of a second. One of the most dramatic examples occurred in 2004, when a magnetar 50,000 light-years away unleashed a flare so powerful it temporarily ionized Earth's upper atmosphere, despite being halfway across the galaxy. Satellites detected the surge as if someone had briefly turned up the sun's brightness by a factor of 100,000. Had this happened within 10 light-years, it could have stripped our ozone layer, triggering mass extinctions. Magnetars don't just flirt with destruction, they redefine it. Yet within this chaos lies eerie precision. Magnetars don't erupt randomly. Their outbursts follow patterns tied to crustal fractures and magnetic reconnection, processes so finely tuned that astronomers can sometimes predict them. The magnetar SGR 1935 plus 21.5, for instance, emits regular X-ray pulses every 3.76 seconds with atomic clock reliability, until it doesn't. Without warning, it might convulse in a storm of flares, ejecting enough energy to power human civilization for billions of years in mere milliseconds. This duality between metronomic stability and apocalyptic fury makes magnetars nature's ultimate wildcards. What's truly humbling is how these monsters test the limits of known physics. A magnetar's magnetic field reaches up to 10 quadrillion Gauss. To grasp that scale, consider Earth's field measures about half a Gauss, strong enough to guide compass needles but weak enough to ignore. A magnetar's field, by contrast, would distort the electron clouds of atoms within 100,000 miles, rendering chemistry impossible. Even light passing through such a field would split into bizarre, polarized paths, a phenomenon predicted by quantum electrodynamics but never observed in nature until magnetars came along. These extreme properties make magnetars cosmic laboratories. When two neutron stars collide, theorists suspect the resulting remnant could briefly become a magnetar before collapsing into a black hole, powering some of the universe's most energetic explosions. Some even propose that certain fast radio bursts, those mysterious millisecond flashes from deep space, could be magnetar tantrums on an intergalactic scale. Every flare, every pulse, every crack in their crust offers clues about matter under conditions no lab could ever replicate. So while pulsars sing the universe's most reliable lullabies, magnetars scream its heavy metal anthems. They remind us that order and chaos aren't just partners, they're shapeshifters capable of trading roles in an instant. One moment, a magnetar is the cosmos' most precise timekeeper. The next, it's a celestial powder keg rewriting the rules of destruction. In their twisted magnetic hearts, we see the universe's true nature, a place where stability is just the calm between tempests, and even the most orderly phenomena hide unimaginable fury. Somewhere in the darkness between constellations, an invisible hand tugs at our galaxy, pulling the Milky Way and its neighbors toward a mystery we can't see. This is the Great Attractor, a gravitational anomaly so powerful it bends the motion of hundreds of galaxies, yet remains hidden behind the dense stars of our own Milky Way's disk. Imagine standing on a riverbank watching leaves float past, all drifting steadily toward some unseen waterfall downstream. That's the eerie reality astronomers face. Entire galaxies, including our own, are streaming toward a point in space we scarcely understand, moving at over 14 million miles per hour toward the unknown. The first clues emerged in the 1970s when astronomers mapping cosmic microwave background radiation noticed something peculiar. The Milky Way wasn't just drifting aimlessly, it showed a distinct velocity toward the constellation Centaurus, as if drawn by some colossal, invisible mass. Later studies revealed this wasn't just our galaxy's private journey. The entire local group, a collection of galaxies including Andromeda along with the Virgo supercluster and thousands of other systems, were all caught in the same cosmic current. Whatever lay at the end of this gravitational conveyor belt had to be unimaginably massive, yet it left no visible trace. Initial theories pointed to the Norma cluster, a dense gathering of galaxies about 250 million light-years away. But calculations soon showed its gravity was a mere ripple compared to the force required. The true Great Attractor, it seemed, was something far grander. Perhaps the Laniakea supercluster, a filamentary web of galaxies spanning 500 million light-years with the attractor near its heart. Here's where the mystery deepens. Laniakea's gravity explains some of the pull, but not all. There's still missing mass, hidden in ways that challenge our understanding of cosmic structure. What makes the Great Attractor so fascinating isn't just its hidden nature, it's the interplay of forces at work. On one hand, this motion is a triumph of gravitational order, a predictable flow following Einstein's equations. On the other, it's a reminder of how much we don't know. Dark matter likely plays a starring role, its invisible scaffolding amplifying the attractor's pull. Some theorists even speculate about exotic possibilities, primordial black holes from the early universe, or rare concentrations of dark energy warping spacetime itself. The truth may lie in the unseen architecture of the cosmic web, where dark matter's tendrils guide galaxies like beads on a string. Efforts to study the attractor face a cosmic irony. Its location lies directly behind the Milky Way's crowded central bulge, a zone astronomers call the zone of avoidance because interstellar dust and stars block our view. It's like trying to spot a mountain through a blizzard. Only recently have infrared and radio telescopes like NASA's WISE mission begun piercing this veil, revealing hints of massive galaxy clusters previously obscured. Each new observation chips away at the mystery, but the full picture remains tantalizingly out of reach. Perhaps the most humbling lesson of the Great Attractor is this: even as we map the universe in ever greater detail, vast unknowns still move us literally. Our galaxy sails toward an enigma, caught in a current older than Earth itself. Whatever lies ahead, one thing is certain: the cosmos still holds secrets that defy even our boldest theories, reminding us that the grandest forces are often the ones we can't yet see. The universe began not with a bang, but with a stretch a fraction of a second so brief it makes the blink of an eye seem eternal. In that sliver of time, space itself expanded faster than light could chase it, doubling in size over and over again until a volume smaller than an atom became larger than our observable universe. This was cosmic inflation, the ultimate cosmic reset button, ironing out wrinkles in the infant cosmos like a celestial steamroller. Picture a crumpled piece of paper suddenly smoothed flat, except this paper is space-time, and the hand doing the smoothing is a mysterious field of energy we've yet to fully understand. What's astonishing isn't just the scale of this expansion, but what it left behind. Quantum fluctuations, tiny, random jitters in the fabric of reality, were caught in the act and stretched to astronomical proportions. These microscopic ripples, no larger than a billionth of a proton, became the seeds of galaxies. The same randomness that governs subatomic particles today once dictated where the Andromeda galaxy would form, or whether the Milky Way would spiral or elliptical. It's as if the universe rolled cosmic dice at its birth, and we're living in the aftermath of that throw. Yet inflation didn't just amplify chaos, it transformed it. The very same process that stretched quantum noise into cosmic structure also erased the universe's rough edges, leaving behind a startlingly uniform cosmos. Look in any direction, and the cosmic microwave background, the afterglow of the Big Bang, shows near identical temperatures, varying by less than 1 part in 100,000. Without inflation, these regions would never have had time to equilibrate, leaving the cosmos patchy and uneven. Instead, we inhabit a universe where the largest structures, galaxy clusters, superclusters, even the vast cosmic web, trace their origins to quantum tremors frozen in time. The evidence for this wild idea isn't just theoretical. When astronomers map the cosmic microwave background, they find patterns that match inflation's predictions with eerie precision. Those tiny temperature variations, they follow a statistical fingerprint unique to quantum fluctuations stretched across spacetime. Even the universe's flat geometry, where parallel lines never meet, points to inflation's relentless smoothing effect. It's as if the cosmos left us a breadcrumb trail of clues, each one more compelling than the last. But inflation's greatest gift might be its paradox. It took the universe's most chaotic moments and used them to build order. Today's majestic spiral galaxies, with their stately rotations and glittering arms, owe their existence to quantum randomness magnified beyond imagination. The same uncertainty that makes electrons flicker in a lab once determined whether a galaxy cluster would form here or a billion light-years away. Inflation didn't erase the chaos, it wove it into the cosmos blueprint, proving that even the universe's most orderly structures are built on foundations of pure chance. So the next time you gaze at the night sky, remember, the stars above aren't just points of light. They're quantum whispers from the dawn of time, stretched across the eons by a force so powerful it shaped reality itself. The universe didn't begin tidy, it became that way. Through a dance of expansion and transformation we're only beginning to comprehend. And somewhere out there, other quantum fluctuations are still echoing, still shaping the cosmos in ways we've yet to discover. There's a moment just before dawn when the sky holds its breath, a hushed interval where the stars begin to fade, but the sun hasn't yet claimed the horizon. In that fragile stillness, if you're far from city lights, you might glimpse something extraordinary, a faint, ghostly pyramid of light rising from the eastern horizon, its base resting on the earth and its tip stretching toward the heavens. This is the Zodiacal light, one of the night sky's most ethereal wonders, and its story is a paradox born from chaos, yet sculpted into perfect order by the silent hand of gravity. The glow you're seeing isn't some distant nebula or far-off galaxy. It's sunlight reflecting off trillions upon trillions of dust grains, each no larger than a speck of flour, drifting in the inner solar system. These particles aren't random debris, they're organized into a vast, lens-shaped cloud centered on the sun, with most concentrated along the ecliptic, the same plane where the planets orbit. Like cosmic breadcrumbs, they trace the solar system's fundamental architecture, a testament to how even the smallest fragments eventually fall in line with gravity's grand design. Where does this dust come from? Look no further than the asteroid belt, where rocky bodies collide in spectacular crashes, or the tails of comets, which shed icy grit as they swing close to the sun. Every time two asteroids slam together at speeds topping 12,000 miles per hour, or a comet's nucleus fractures under solar heat, fresh debris joins this interplanetary haze. These events are anything but orderly. Imagine a demolition derby in slow motion, with shrapnel flying in every direction. Yet over millennia, solar radiation and gravitational nudges from planets like Jupiter shepherd these particles into stable orbits, smoothing their chaotic origins into a serene, luminous band. The zodiacal light isn't just a pretty glow, it's a cosmic fossil record. By studying its spectrum, astronomers have uncovered surprises. Some dust grains bear signatures of water and organic molecules, likely carried inward by comets from the solar system's frozen outskirts. Others show crystalline structures that only form in extreme heat, hinting at violent pasts involving asteroid impacts or volcanic eruptions on long-dead worlds. Each speck is a time capsule, preserving clues about the solar system's tumultuous youth. What's truly remarkable is how this delicate balance persists. Without constant replenishment, the zodiacal dust would spiral into the sun within 100,000 years, drawn inward by a process called Poynting-Robertson drag. Yet the light has shone for billions of years, a sign that the solar system's chaotic factories, colliding asteroids, disintegrating comets, keep pace with the loss. It's a self-regulating system where destruction and renewal dance in lockstep. So the next time you spot that faint pyramid in the pre-dawn sky, remember, you're not just seeing dust. You're witnessing the afterlife of cosmic violence, transformed by time and gravity into a beacon of tranquility. The universe has a way of turning chaos into art if we're patient enough to watch it unfold. Imagine two city-sized stars, each so dense a teaspoon of their material outweighs Mount Everest, locked in a death spiral. As they draw closer, their immense gravity stretches space-time itself, sending ripples across the cosmos at the speed of light. Then collision. The impact unleashes energy equivalent to 1 billion suns, ejecting jets of superheated matter laced with neutrons at nearly light speed. This is a kilonova, the universe's most spectacular forge, where chaos becomes creation in the blink of an eye. What makes these mergers so extraordinary isn't just their violence, it's what they leave behind. The ejected material, hotter than the sun's core and denser than an atomic nucleus, becomes a crucible for elements heavier than iron. In ordinary stellar furnaces, these elements can't form. Fusion stops at iron because absorbing energy rather than releasing it. But here, in the neutron-rich debris of a kilonova, a process called rapid neutron capture, or the R process, takes over. Atomic nuclei gulp down free neutrons like celestial Pac-Men, growing heavier and more unstable until they decay into stable forms. Gold, platinum, uranium, the very elements that glitter in jewelry stores and power nuclear reactors, are born in this maelstrom. The first direct proof came in 2017, when gravitational wave detectors LIGO and Virgo caught the tremors from a neutron star merger 130 million light-years away. Within hours, telescopes worldwide swiveled toward the source, capturing something never seen before. A kilonova's afterglow, its light tinged with the spectral fingerprints of heavy elements. Calculations suggested this single event produced enough gold to outweigh Earth several times over. Suddenly, the mystery of where half the universe's heavy elements come from had an answer, written in gravitational waves and starlight. Yet the alchemy doesn't stop at creation. These freshly minted atoms, flung into space at relativistic speeds, eventually mix with interstellar gas. Over eons, gravity gathers this enriched material into new molecular clouds, where it becomes part of nascent solar systems. The gold in your wedding ring might have cycled through multiple generations of stars before landing in that kilonova's ejector, then spent billions of years drifting until Earth's formation swept it up. Every precious metal on our planet, every platinum catalyst, every uranium fuel rod, carries echoes of neutron stars' final embrace. Kilonovas don't just make elements, they distribute them with cosmic precision. Simulations show their ejector form intricate, expanding tendrils like a spiderweb spun in hyperdrive. This structure ensures heavy elements don't clump too densely, allowing them to pepper star-forming regions evenly. Without this efficient dispersal, planets like Earth might lack the metallic diversity needed for complex geology or life. The same chaos that forged these elements also ensures they're scattered just right, threading the needle between abundance and accessibility. Perhaps most poetically, these collisions are vanishingly rare. In our galaxy, they might occur once every 10,000 to a million years. Yet across the universe's vast timescales, they've seeded countless worlds with the ingredients for technology, art, and wonder. The gold in King Tut's mask, the platinum in a Mars rover's circuits, even the uranium fueling reactors, all were born in moments of unimaginable destruction, transformed by time and gravity into treasures. The universe doesn't just balance chaos and order, it spins straw into gold, proving that even its most violent acts are part of a grand creative dance. The universe has a speed limit, the Hubble constant, a number that tells us how fast space is stretching apart, or at least it should be constant. But here's the cosmic curveball. Depending on how we measure it, we get two different answers and they refuse to agree. This is the Hubble Tension, a discrepancy so stubborn it's shaking the foundations of modern cosmology. One method, using the cosmic microwave background, the afterglow of the Big Bang, suggests the universe expands at about 67 kilometers per second per megaparsec. Another, based on the flicker of distant stars and supernova, pegs it closer to 73. At first glance, that gap seems small, just a few digits apart. But in the precise world of astrophysics, it's a yawning chasm, one that might demand rewriting physics itself. So where does this rift come from? The simplest explanation is human error. Maybe we're misreading the cosmic yardsticks. But after years of cross-checking, with teams worldwide refining measurements using everything from gravitational lensing to pulsating stars, the gap hasn't closed. It's widened. That leaves a far more thrilling possibility. Our understanding of the cosmos is missing something fundamental. Dark energy, the mysterious force accelerating the universe's expansion, might not be constant as we assumed. It could evolve over time, growing stronger or weaker in ways we haven't accounted for. Or perhaps dark matter, the invisible scaffold holding galaxies together, interacts in stranger ways than our models predict. Then there's the wild card, new physics altogether. Could extra dimensions, hidden forces, or even flaws in Einstein's relativity be warping our cosmic calculations? Some theorists toy with the idea of early dark energy, a surge of repulsive force that briefly dominated the infant universe, leaving echoes in today's expansion rate. Others suggest the universe isn't as uniform as we thought, with vast bubbles of underdense space tugging measurements askew. Each hypothesis is a shot in the dark, but that's the beauty of the tension. It's a crack in the facade, a glimpse of the unknown lurking behind our tidy equations. What makes this more than an academic debate is what it reveals about cosmic order. For centuries, we've sought rules to explain the heavens, from Newton's gravity to quantum mechanics. But the Hubble tension reminds us that the universe isn't obliged to fit our models. Like a dancer improvising mid-routine, it might follow rhythms we've yet to hear. Every conflicting measurement, every stubborn digit is a clue, a whisper that the grand choreography of the cosmos holds steps we haven't learned. Until we do, the Hubble tension isn't just a problem to solve. It's an invitation to look deeper, to question harder, and to remember that the universe's greatest mysteries often hide in plain sight. The sun isn't just a steady beacon in our sky, it's a roiling sphere of plasma, where magnetic fields twist into knots tighter than any sailor could tie. When these fields snap like overstretched rubber bands, they unleash solar flares, bursts of energy so powerful they can outshine 1,000,000 atomic bombs. In mere minutes, a single flare can hurl charged particles across 93 million miles of space, straight toward Earth. We're shielded by our planet's magnetic field, but the effects still ripple through our technology. Satellites hiccup, radio signals scramble, and power grids shudder under the invisible assault. The Carrington event of 1859, a solar storm so strong it set telegraph wires ablaze, was a wake-up call. If a flare like that struck today, it could plunge continents into darkness for months. Yet for all their unpredictability, solar flares aren't entirely lawless. They follow an 11-year cycle, a rhythm as reliable as the tides. During solar maximum, the sun becomes a tempest, peppering space with flares and coronal mass ejections. At solar minimum, it calms to a simmer. This cycle isn't arbitrary, it's tied to the sun's magnetic field, which flips polarity like a cosmic metronome every 11 years. Even chaos, it seems, has a schedule. What's fascinating is how this dance between turmoil and order plays out on our star's surface. Sunspots, those dark blemishes on the solar face, are ground zero for flares. They form where magnetic fields punch through the sun's surface, trapping superheated plasma in loops taller than Earth. When these loops tangle and reconnect, the energy release can heat plasma to tens of millions of degrees, launching flares at nearly light speed. The same forces that light up auroras over the poles also threaten the delicate electronics we rely on daily. Modern astronomy lets us watch this ballet in real time. NASA's Solar Dynamics Observatory captures flares in ultraviolet wavelengths, revealing intricate structures that writhe like living things. The Parker Solar Probe dives through the sun's corona, tasting the charged particles mere hours after they erupt. Each new observation peels back another layer of mystery, showing us how a star's tantrums shape the space around it. The lesson here isn't just about preparing for the next big flare, though that's vital. It's about recognizing that the cosmic dance isn't some distant spectacle. The sun's fury and grace are woven into our lives, from the satellites guiding our phones to the very light that keeps our planet alive. Chaos and order don't just exist out there. They're right overhead, painting the sky with fire and reminding us that we're part of something far grander than our daily routines. In 1961, astronomer Frank Drake wrote a single equation on a chalkboard that would forever change how we ponder life among the stars. At first glance, it looks deceptively simple, just 7 variables multiplied together. Yet this elegant string of symbols, now known as the Drake equation, encapsulates one of humanity's most profound questions: are we alone in the universe? What makes the equation remarkable isn't just what it calculates, but how it bridges cosmic chaos with mathematical order. Take the first variable, the rate of star formation in our galaxy. On any given night, telescopes capture the fiery birth of new suns in sprawling stellar nurseries like the Orion Nebula. These events seem random, governed by turbulent gas clouds collapsing under their own weight. Yet zoom out over cosmic time and patterns emerge. The Milky Way produces about 3 new stars annually, a surprisingly stable figure that anchors the equation's first term. This interplay repeats throughout the formula. The fraction of stars with planets draws from the chaos of protoplanetary disk formation, yet Kepler Space Telescope data shows nearly every star likely hosts worlds. The real magic lies in how Drake's framework transforms uncertainty into structure. Consider the factor for habitable planets per system. We've found worlds orbiting binary stars, rogue planets drifting between galaxies, and super-Earths with crushing gravity. The possibilities seem endless until the equation reminds us to quantify. When astronomers plug in current estimates, they find perhaps 1 in 5 Sun-like stars hosts an Earth-sized planet in the habitable zone. That's not random guessing, it's chaos filtered through data. Then comes the most speculative leap, life's emergence. The famous Miller-Urey experiment showed amino acids, life's building blocks, can form spontaneously in conditions mimicking early Earth. But does this happen on other worlds? Europa's subsurface ocean and Titan's methane lakes suggest the ingredients exist beyond Earth, yet we've never detected extraterrestrial life. The equation acknowledges this uncertainty by making biology a variable rather than a constant, allowing our estimates to evolve as science progresses. What truly elevates the Drake equation from mathematical curiosity to cultural icon is its philosophical weight. By assigning numerical values to cosmic probabilities, it transforms our search for company in the void from wishful thinking into a measurable endeavor. SETI radio telescopes scan the stars not at random but guided by the equation's framework. Each failed detection refines our estimates, narrowing the possibilities. The equation's final terms, civilization lifespan and communication capability, hold a mirror to humanity. How long does technological society last before collapse? A century, a million years, this variable remains blank not because we lack cosmic data, but because we're still writing the answer through our choices. The Drake equation doesn't just calculate aliens, it measures our own place in the universe's grand story, reminding us that order and chaos dance together in the search for meaning among the stars. The universe isn't just a place, it's a performance, an endless dance where chaos and order twirl together in perfect synchrony. Think of the last time you looked up at the stars, tracing the familiar patterns of constellations. Those stars seem fixed, eternal, yet everyone is hurtling through space at unimaginable speeds, born from violent supernova and nursed by the gentle pull of gravity. This is the cosmic dance in its purest form, chaos forging beauty and order preserving it long enough for us to witness. Consider something as simple as Earth's orbit. Our planet doesn't just wander aimlessly around the sun. It follows an elliptical path so precise we can predict its position centuries from now. Yet this stability emerged from chaos. 4.5 billion years ago, our solar system was a swirling disk of gas and debris, a celestial demolition derby where planets jostled for position. Through countless collisions and gravitational nudges, the chaos settled into the rhythmic harmony we take for granted today. The same turbulence that once scattered now binds, proving that disorder isn't the enemy of order, it's the raw material from which order emerges. This dance plays out at every scale. Inside a star's core, the chaotic frenzy of nuclear fusion produces the steady light that nurtures planets. In the quantum realm, particles flicker in and out of existence unpredictably. Yet their behavior follows mathematical laws so precise we can build computers around them. Even the Milky Way's elegant spiral arms, those stately swirls of stars and gas, are shaped by shock waves from supernova cataclysms that somehow sculpt symmetry from the storm. The universe doesn't choose between chaos and order. It needs both, like a composer needs both dissonance and resolution to create a symphony. What's truly humbling is how deeply this duality runs in us. The iron in your blood, the calcium in your bones, these elements were forged in the depths of massive stars, scattered across space by explosions, then gathered by gravity into the rocky planet we call home. Your very existence is a product of chaos harnessed by order, a testament to the universe's ability to create meaning from randomness. When astronomers search for life beyond Earth, they're not just looking for water or the right temperature. They're searching for worlds where this dance has struck the same delicate balance. So the next time you feel overwhelmed by life's unpredictability, remember, the cosmos thrives on this tension. Without chaos, stars would never ignite. Without order, they'd burn out in an instant. The universe doesn't eliminate randomness, it choreographs it, turning turbulence into galaxies, supernova into stardust, and quantum jitters into the building blocks of reality. We are both witnesses and participants in this grand performance, living proof that chaos and order don't just coexist, they create. Now it's your turn. When you look at the night sky, where do you see this dance playing out? Is it in the unpredictable streak of a meteor or the steady pulse of a distant pulsar? Share your thoughts below, and if you've enjoyed this journey through the cosmos' greatest duet, don't forget to subscribe. The universe has infinite encores, and we're just getting started.